So 1.4, equivalent equations. An equation has an infinite number of equivalent forms. An equation has an infinite number of equivalent forms. What does that mean? That means I can write the same equation in many different ways. And we're going to check this out by example and investigation. So for instance, I can take the equation x plus y equals 6. Well, let's make a table of things that satisfy this equation. We'll make a table of values that satisfy this equation. So we have our x values and our y values. Well, what happens when we sub in x equals 1? Maybe I can rewrite this, put this in a form that we like to use. We'll put it in y equals form. So I need to subtract x from both sides. So I'll be left with y equals 6 minus x. So if y equals 6 minus x, and I sub x equals 1 into the equation, Amy, what will the y value be? I've got x equals 1. What will the y value be? Equals? Okay, so y equals 6 minus 1, so the y value is 5. What if I sub in x equals 2? Gavin? So I'm just putting x equals 2 into my equation. So y equals 6 minus 2. 4. Good. Ness, x equals 3. Corresponding y value will be 3. Sarah, x equals 4. 2. Good. So we have enough coordinates here. We have enough x's and y's that satisfy the equation x plus y. These are called ordered pairs, okay? So now the ordered pair for this, maybe I can write it here. The ordered pair for this, do you guys have enough room, hopefully, to do this, to extend your chart? The ordered pair here is 1, 5. Next would be 2, 4. Remember, this is just the x value with the y value. Another ordered pair that satisfies the equation is 3, 3. And the last ordered pair that satisfies this equation is 4, 2. There are plenty more, but these are the only things that we need in order to test what we're saying here. So now let's find an equivalent equation to y equals 6 minus x, or x plus y equals 6, because these are the same equation, just in different forms. But let's see what happens now. Hopefully you still have space to go that way. Let's see what happens now if we change this equation a little bit. We're going to multiply each of the terms in this equation by 2. So we're going to take the y and multiply it by 2. Then we're going to take the 6, multiply it by 2. And this negative x and multiply it by 2. So let's put that in our chart. 2y equals 12 minus 2x. Now, let's find out what y is going to equal, or sorry, let's find out if each of these ordered pairs is still going to satisfy our new equation. Okay, so all we're going to do is plug in the ordered pair that we got from our original equation into our second equation. That looks like this. Instead of 2y, we have 2 times 5. And we're hoping that it's going to equal 12 minus 2x, where x is 1. So my left side is 2 times 5 is 10. My right side is 12 minus 2, which is 10. Did it work? It did. If the left side is equal to the right side, then that means it's a true statement, which means that these ordered pairs satisfy this equation and they satisfy this equation. Here? Yeah, 2 times 1 because the x value that we put into the equation was 1. Okay? All right, let's see what happens when we put in the x value of 2 and a y value of 4. So we have 2 times 4, and we're hoping that it's going to be equal to 12 minus 2 times x, which is 2. So on the left side, 2 times 4 is 8. And on the right side, 2 times 2 is 4. 12 minus that 4 is 8. This is still true, so we know that the ordered pair 2, 4 satisfies our original equation as well as the equation that we multiplied every term by 2. And you guessed it, we could do the next two, and they would also be true statements. These x and y's, 3, 3, and 4, 2, will also satisfy our second equation, just like they did our first equation. That makes these two equations equivalent. They're the exact same. Any x and y, any ordered pair that satisfies this equation will satisfy this equation. If that's true, they're equivalent. If they're equivalent, that will be true. All right, we're going to try to make another equivalent equation by multiplying each of these terms by -3. So instead of y, we're going to have -3y. Instead of 6, we're going to multiply 6 by -3. That's -18. And instead of -x, we're going to have -x times -3, which is positive 3x. I'm going to write that in my chart. -3y equals -18 plus 3x. And I'm going to check a couple of the ordered pairs. So let's see what happens if we sub in x equals 1 and y equals 5. How will I know if it's an equivalent equation? Yeah, if the coordinates or if the ordered pair 1, 5 satisfies the equation, then it should be equivalent. But I have to check more than one point. It could just be a point of intersection. So in order for it to be the exact same equation, actually all the ordered pairs would have to match up. So let's try. We've got -3 times 5, and we're hoping that it's equal to -18 plus 3 times 1. -3 times 5 is -15. 3 times 1 is 3. So we do have -15 equals -18 plus 3. So I'm at -18, but I'm going to bounce toward 0 3 bounces. That's going to be -15. And that's a true statement. So the ordered pair 1, 5 does satisfy this equation. I can jump down here to this ordered pair. We know it satisfies our original equation. Let's see if 4, 2 will satisfy our new equation. We've got -3y, which is 2, equals -18 plus 3x, which is 4. -3 times 2 is -6. 3 times 4 is 12. And now on the right-hand side, I have -18 plus 12. That's -6. So that checks out. Okay, so if I have an equation like x plus y equals 6, how can I develop another equivalent equation? How can I develop an equation that is equivalent to x plus y equals 6? What could I do? I need to multiply every term in the equation by the same value. Okay, so a note. To develop an equivalent equation, multiply all the terms of the original equation by the same value. To develop an equivalent equation, multiply all the terms of the original equation by the same value. Could I multiply by a fraction? Yes, I could. Multiplying by a fraction is the same as dividing. So I could actually divide every term by the same value, and I would still get an equivalent equation. And that becomes very helpful if you start with something like this. You don't want to work with an equation like negative 3y equals negative 18 plus 3. That's an ugly equation to work with. But you could divide each of these terms by negative 3, and you would end up with this equation. And every single ordered pair, every single x and y that go together for this equation will also work together and be a solution for this equation. So on textbook, page 24, you'll find investigation 1.4. In part 1, try number 5, A and C. It says write 3 equations that are equivalent to each of the following equations. Okay, so we're looking at part 2, equivalent systems. On page 24, we have system A. System A involves x minus y equals 3 and x plus y equals 7. We need these both to be in y equals mx plus b. So you go ahead and put them in the standard form for a line, which is y equals mx plus b. Okay, you should have over here, if you subtracted y to the other side and you subtracted 3 to this side and then rearranged it, you should be left with y equals x minus 3. And that's equation 1. And equation 2, you just subtract x to the other side, subtract x from both sides, sorry, y equals 7 minus x, or negative x, probably easier for us to do, negative x plus 7. Those all mean the same thing. Yep, so that's why I changed it down here to say the x first. Yeah, so this is the form that helps us the most. It tells us the slope is negative 1 and tells us the y-intercept is positive 7. So why don't we go ahead and draw number 2 first, since we're talking about it. The y-intercept is positive 7, so 1, 2, 3, 4, 5, 6, 7. That's where it's going to cross the y-intercept. And the slope is -1. So rise over run, it's going to go over 1, down 1, over 1, down 1, over 1, down 1, over 1, down 1. And that should be enough dots for me to draw a straight line. Yep. So the y-intercept happens where x equals 0. So x equals 0 along this whole line, right? Which means if I put 0 in here, what would y be? Well, y would be 7. So I know that the point 0, 7 is on the graph. So I start there. Yep, it crosses the x-axis as well. A line always will. Nope, we don't know the answer to that one. So the slope comes right before the x, right? If we're in the form y equals mx plus b, then m tells us the slope, which is -1. So rise over run, I will go over 1 and then down 1. Instead of, this would be a slope of 1, right? Over 1, up 1, over 1, up 1, over 1, up 1. This is a slope of -1. Over 1, down 1, over 1, down 1, over 1, down 1. And let's graph system number 1. You can go ahead and graph it, and then I'll draw it in a second, and you can check your answer. Amy, where is equation 1 going to cross the y-intercept, the y-axis? It's going to cross at -3, okay? If x was 0, which it is for this whole line, if I put x equals 0 in there, then y would equal 0 minus 3, -3. So this point is for sure on the graph of this line, 0, -3. And now, Nadia, what's the slope? 1. M is 1, right? 1 times x. We have a little imaginary, it's not imaginary, it's invisible. Invisible 1 there. So, over 1, up 1, over 1, up 1.
How did you get the other 1? Like, I know that you have the 1 that's like, how do you get, so the 1 is the y, so what's the 1? Like, is it always the same number?
So 1 is the same as 1 over 1. Rise over run.
So if it would be 2, then it would be over 2, up 2, over 2, up 2.
2 is the same as 2 over 1. Rise over run. So now it would rise twice as fast as it would run. So now it would be going up 2 over 1. Oh, you can't even see that anyway. Up 2 over 1. And it would be a much steeper line. All right. Back to drawing our graph. We have our two systems, and as always, we want to label them. This line that we just drew was y equals x minus 3. The first line that we drew was y equals -x plus 7, or 7 minus x, however you like to name it. And now we need to graph system B. Well, system B doesn't have very many options. X is going to be 5, and y is going to be 2. So 1, 2, 3, 4, 5. X is going to be 5, and y is going to be 2. What do you notice? That's where the lines intersect, right? So does system B satisfy system A? Yeah. Okay. One more note. So part 3. Adding equations. And they give you the two equations. They give you equation 1, which is x.
All under the equation?
Yes. Yep. X plus 2y equals 4. And x minus y equals 1. Now when you're adding equations, you kind of want your terms to be lined up underneath each other and your equal sign to be lined up underneath each other. And what it says to do is add equation 1 and equation 2 to form a new equation. And it tells us exactly how to do that. We're going to add the left sides together, and then we're going to add the right sides together. Okay? So we can do this just like any old addition problem. We've got x plus x. What is x plus x? 2x. We've got 2y plus negative y. So that's the same as saying 2y minus y. It's just one y. So we have plus y. And on the right side, 4 plus 1 equals 5. Why is it positive y? Was that the question? Yep, because here we have two y's, y, y, and we're subtracting one of the y's. So that leaves us with one y left over. Good question. So now we have equation 1, equation 2, and we have created equation 3. And we are asked to graph each of these 3 lines on the same set of axes. So before we do that, what do you think is going to happen if we graph these lines on the same set of axes?
Do you ever have to add fractions?
Yes. Okay, ready? We're going to get each of these lines in the form y equals mx plus b. Okay, so number 1 is going to become, I'm going to subtract x from both sides, and then I'm going to divide it all by 2. Can you see that? I need to get y by itself, I need to first subtract x from both sides, then I need to divide all the terms by 2 to get y by itself. Yeah, so I'm going to do those 2 steps right away. This is going to be, so the right side first becomes 4 minus x. Then I'm going to divide it all by 2. So 4 divided by 2 is 2, and x divided by 2 is 1/2 x. So that's so the 2 is stuck to the y right now. So I'm doing two steps in one. So I'm subtracting x from both sides. So I'll have 4 minus x. Then I'm dividing all the terms by 2 so that I can get y by itself. Okay? So y is going to equal negative 1/2 x plus 2. It's okay. You don't have to do the math on that one. You can just trust it. Yes. Now I put it in the right form, y equals mx plus b. Equation 2, I have negative y. So I'm going to add y to both sides, and I'm going to subtract 1 from both sides. So I'm going to have y equals x minus 1. Equation 3 is not in y equals mx plus b form, but it's a little bit easier to do. I'm just going to subtract 2x from both sides.
If you subtract 2 from x, then you get x.
I'm not subtracting. I'm subtracting 2 x's.
But don't you want just x by itself?
No, I want y by itself.
But don't you want x by itself too, or no?
If I needed to solve this algebraically, then I would now substitute y into one of these equations, and then I would solve for x, try to get x by itself. But right now, I need to draw lines, right? I have my graph out, I'm ready to draw some lines. This is the equation of the line. Y equals mx plus b. So here we go. This is where I wish I had more colors.
You could graph all 3 lines.
Graph all 3 lines. Okay? X, Y. Girls. Okay, hopefully you've tried this on your own already. I have drawn line number 1, a few points on line number 1. It has a y-intercept of +2, and then it is going to go down 1 and over 2 each time. So I've gone down 1 over 2, down 1 over 2. And that is enough information to draw our line. Line number 1, drawn. Line number 2 has a y-intercept of, Amy? Has a y-intercept of -1. And Gavin, it has a slope of this equation. Equation number 2 has a slope of, what's the slope? What's the m in front of the x? Yep, slope of 1. So up 1 over 1, up 1 over 1, up 1 over 1.
Oh, I understand. Can you only do 1 dot and then just draw a line?
Nope.
No?
You should for sure do like 3 or 4.
The one on the y, and then just draw 1 and then draw
You could, but that leaves the option that you might have made a mistake. So if you draw a 3rd dot and the 3rd dot confirms the first 2 dots, then you have done it correctly. Okay?
Wait, but it's negative, so don't you have to go down?
This has a positive slope. The intercept is -1.
1 up, and you only draw the dots on the y, right? No, on the y.
Okay, let's draw number 3 together, please. Y equals -2x plus 5. So the intercept here, the y-intercept is +5. And I have a slope here, Nadia, of a slope of -2. Okay, so rise over run, that's -2 over 1. That means it's going to be dropping 2 every time it goes over 1. It's going to drop 2 every time it goes over 1. It's going to drop 2 every time it goes over 1. And we can draw our line.
Be quiet, it's not even funny anymore.
Okay, so we had line number 1, we had line number 2, and now we have equation number 3. What do the 3 lines have in common? Ness, what do the 3 lines have in common? Yeah, they meet. They all intersect at the same point. So that means that these 3 lines have the same solution. Okay? So this system, the solution for this system is the point 2, 1. 2, 1 is a solution of this system. And this third one was actually an addition of the first two. So we didn't even know this third equation until we added equation 1 to equation 2. So if you need to find the point of intersection, okay, last note. We already took a note on equivalent equations. This note is on equivalent systems. We didn't take a note though.
No, it's still on 1.4, right?
An equivalent system should say a system is equivalent to systems. Two systems are equivalent. It's the same lesson. It's the last sentence you're writing. Two systems are equivalent if they have the same solution.
I'm not.
That means
Not.
if they have the same point of intersection. It's not number anything, it's just a note.
So you gotta pick one thing every week.
Homework is 1.4 worksheet number 1, B and C, 2, B and C, and 3, A, B, and C.